If you've been tracking 3D generative AI, you've likely hit the same wall I have. Models like Trellis-2 or Hunyuan 3D can produce surprisingly coherent geometry, but ask them to reproduce something as straightforward as a plaid shirt, a printed logo, or intricate embroidery, and the texture completely collapses. The shapes are structurally sound, but the surface looks like a smeared watercolor painting. Why? Because high-quality 3D training data is incredibly scarce, while the internet is saturated with billions of 2D images and videos. Ink 3D solves this by making a deliberate architectural shift. It completely decouples geometry from texture and treats texture synthesis as a dense multi-view video generation problem. Instead of forcing a single 3D diffusion model to learn both structural layout and high-frequency appearance from limited data, Ink 3D splits the pipeline into two distinct phases. First, it uses an off-the-shelf geometry estimator to generate a clean, white mesh representation of the object. Then, it leverages the massive visual priors of large-scale video generative models to paint that mesh. The framework consists of two core components: OrbitPainter, a conditional video model that generates dense 36-degree orbit scans, and Texture Optimizer, a neural baking module that fuses those views into a coherent texture map while actively correcting geometric misalignments. Let's start with OrbitPainter. The core insight here is that video models inherently understand three-dimensional consistency because they're trained on continuous camera motion. OrbitPainter takes your reference image and the white mesh geometry and generates two orbit scan videos, one horizontal and one vertical, each containing 61 frames at 500 by 500 resolution. This yields 122 densely sampled views of the object. To train this, they use a flow matching objective rather than traditional score distillation. The model is conditioned on two distinct priors. First, a two-dimensional appearance prior extracted from your reference image. Second, and this is critical, explicit three-dimensional geometric priors. They render surface normal and three-dimensional position videos of the white mesh and concatenate them channel-wise with the noisy latent video during the denoising process. This gives the transformer direct spatial guidance. But the real architectural innovation is a module they call Geometry-Aware Sparse Attention, or GASA. In standard video transformers, every frame attends to every other frame across space and time. That's computationally expensive and ignores the underlying mesh structure. GASA changes this. During attention computation, each spatiotemporal token is reprojected back into three-dimensional space using its associated position map. The model then only attends to tokens that correspond to the same or nearby surface locations across different frames. By restricting the attention window to geometrically consistent regions, GASA enforces cross-view consistency natively, eliminating the color bleeding and pattern drift that usually plagues multi-view generation. Once you have those 122 dense views, you need to bake them onto the white mesh. A naive approach would just average project the pixels onto the surface, but that fails miserably. Video generation isn't perfectly geometry consistent. Slight warping or perspective shifts mean that pixels projecting to the same three-dimensional point often disagree in color or pattern, causing severe blurring and color bleeding. Ink 3D handles this with Texture Optimizer, a training-free neural baking strategy. First, it converts the dense view images into a textured voxel representation. They formulate this as a graph matching problem over a 6-connected voxel graph. Using a Markov random field optimization with alpha expansion, the system assigns each voxel to the single best pixel from the candidate views. The optimization balances a data term that checks geometric visibility and viewing angle against a smoothness term that penalizes seams when adjacent voxels pull colors from different views. But they don't stop there. They take those optimized textured voxels, encode them with a three-dimensional VAE, add a small amount of Gaussian noise, and feed them into Trellis-2 for a few steps of prior guided denoising. This is a clever use of existing models. Trellis-2 was originally trained to denoise completely random geometry into a textured asset. By initializing it with mildly noisy, graph-optimized voxels, you skip the hard part of geometry learning and let the model focus purely on refining high-frequency texture details and fixing residual artifacts. The result is a fully textured three-dimensional asset that actually matches the reference image. The quantitative results speak for themselves. Across standard metrics like FID, ClipFID, LPIPS, and ClipI, Ink 3D significantly outperforms Trellis-2, Hunyuan 3D Paint, and sparse view methods like SecTex and Paint 3D. The ablation studies really highlight why the design choices matter. When you remove the three-dimensional position prior, performance drops sharply because the model loses its spatial anchor. When you disable GASA, you get noticeable cross-view inconsistencies, proving that geometrically constrained attention is necessary for high-fidelity texturing. They also show that higher video resolution and more frames improve texture quality, but naturally increase compute time. On an H100, generating the two orbit videos takes about 12 minutes, though acceleration techniques like DMD2 can cut that down to 2 minutes. Ink 3D represents a fundamental shift in how we approach three-dimensional generation. Rather than fighting the data scarcity problem with larger 3D models, it sidesteps it entirely by borrowing massive visual priors from video generation and translating them into three-dimensional space through dense orbit scanning and neural baking. It's a clean, modular pipeline that proves decoupling geometry and texture isn't a compromise, it's an optimization. For anyone building or researching 3D generative systems, this framework shows that the future of complex texture synthesis lies in leveraging continuous video priors and geometrically aware attention mechanisms. If you want to dig into the math, check out the paper and the open source repository linked below. Thanks for watching, and I'll see you in the next one.